What would happen if you drilled through the Earth? Intense pressure and sweltering temperature would accompany a trip down through Earth's layers and out through the other side. However, this trip would be possible only, of course, in science fiction. Earth's many layers are hidden from view, but what if we could drill through center of the planet to the other side? What extreme forces and temperatures would we encounter deep within the planet? Even though drilling through Earth remains science fiction, scientists have some ideas about what might occur based on experience from other drilling projects. Earth's diameter is 7,926 miles, or 12,756 kilometers. That's from end to end. So drilling all the way through the planet will require a gargantuan drill and decades of work. The first layer to drill through is the crust, which is about 60 miles thick, according to U.S. Geological Survey. The atmospheric pressure would increase as the drill traveled farther underground, and every 10 feet or 3 meters of rock is equal to about 1 atmospheric pressure. The pressure at sea level, Doug Wilson, a researcher geophysicist at University of California, Santa Barbara, told Live Science, he said that adds up really quick when you're talking about a large number of kilometers. The deepest human-made hole today is the Kola Super Deep borehole in Russia, which is 6.7 miles deep. At its bottom, the pressure is 4,000 times that at sea level. It took scientists nearly 20 years to reach this depth, according to World Atlas, and that's still over 50 miles away from the next layer, the mantle, according to Earth's layer data from USGS. The mantle is 1,740 miles thick, layer of dark, dense rock that drives plate tectonics. The boundary between the mantle and the core is called the MOHO, short for Moho-Rovicki discontinuity. Scientists first attempted to dig here through the deep seafloor in the 1950s and 60s with Project MOHOLE, but they were unsuccessful. The hole made in the quest to drill through the planet would cave in unless we continuously pumped drilling fluid into the hole. And deep sea and oil well drilling, that fluid is a mix of mud that includes heavy minerals like barium. The weight of the fluid balances the pressure inside the hole with the pressure of the surrounding rock, and thus prevents the hole from collapsing, Wilson explained. The drilling fluid serves to two additional roles. It cleans the drill bit to prevent sand and gravel from gunking up the machinery, and it helps lower the temperature, although it would become nearly impossible to keep the drill cool in Earth's innermost layers. For instance, the temperature in the mantle is a searing 2,570 degrees Fahrenheit, that's 1,410 degrees Celsius. Stainless steel would melt, so the drill would need to be made of expensive, specialized alloy like titanium, Wilson said. Once through right through the mantle, the drill would finally reach Earth's core at about 1,800 miles. The outer core is made mostly of liquid iron and nickel and is extremely hot, with temperature ranging from 7,200 to 9,000 degrees Fahrenheit, according to California Academy of Science. So drilling through this hot molten iron-nickel alloy would be especially difficult. That would cause a whole range of issues, Davin Teagle, professor of geochemistry, University of Southampton, the UK, said. The fiery outer core would be like drilling through a liquid, and it would likely melt the drill unless cold water was pumped down. And then after 3,000 miles, the drill would reach the inner core, where the pressure is so intense that despite the scorching temperatures, the nickel and iron core remains solid. You'll have to be at indescribable pressures, Teagle said. About 350 gigapascals, or 350 million times atmospheric pressure. This whole time the drill would be pulled down to the core by Earth's gravity. In the center of the core, the gravity would be similar to being in orbit, effectively weightless. That's because the pull of Earth's mass would be equal in all directions, Wilson said. And then, as the drill continues towards the other side of the planet, the pull of gravity will switch relative to the position of the drill, effectively pulling it down towards the core yet again, and the drill will have to work against gravity as it pushes up towards the surface, back through the outer core, mantle, and crust to reverse the downward journey. If all these obstacles are overcome, the biggest problem once you reach the midpoint is that you'll still have a long way to go to reach the other side, Teagle said. And this is by Hannah Loss on Life Science. Please leave your comments. Thank you for your support. My Patreon account, the daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.